Okay, hello everyone. Welcome to the webinar series by Center for Pre-University Studies. Today we are having our speaker, which is Dr. Muhammad Helmi bin Abdul Mubin, one of the lecturer in Center for Pre-University Studies. He will talk about the nanomaterials. So basically, in this webinar, he will focus on providing the introduction to nanomaterials, as the main topic of the discussion will be an overview of what nanomaterials are. Subsequently, the webinar will cover the various techniques used for fabricating or synthesizing nanomaterials, as well as exploring their application. Dr. Helmi, in 2010, he obtained a bachelor degree in industrial physics, followed by a master degree in 2014, and finally completing his PhD in material physics in 2018. So throughout his academic journey, he gained extensive expertise in conducting research, particularly in the field of nanomaterial synthesis. Presently, he works as a physics lecturer at the Center for Applied Studies in MAHSA University. Let's welcome.
Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. So thank you, Madam Nodiana, for the nice introduction. So my name is Muhammad Helmi bin Abdul Mubin. So I'm one of the physics lecturer and the Center for Pre-University Studies. So today let me introduce to you the introduction to nanomaterial. Okay, so before we start, so what exactly is the nanomaterial? Why the nanomaterial is important in this 21st century? So first, what is the nanomaterial itself? Okay, in terms of definition, the nanomaterial will use the small object, okay, or small material in order for you to solve a big problem, right? And then from the nano, from the Greek word mean nanos, okay, or dwarf. You know what is nanos or dwarf is refer to something which is small, okay? And the nanomaterial actually a study development of material where it aims to control, okay, we control and we design the nanomaterial specifically in the size ranging from 1 nanometer to 100 nanometer. So whatever is below than 100 nanometer, we can call as a nanomaterial. So the size is very important to determine the nanomaterial. Okay, if you can see here, we do have a scale here. So the nanomaterial, okay, if you can see, is up to a virus 150 nanomaterial. So bigger than a virus or 100 nanometers, we can call as a micrometer or millimeter up to a meter size of a football. All right. Okay, so I can divide or we can divide the nanomaterial into two categories. The first category is the natural nanomaterial. What is the natural nanomaterial? Natural nanomaterial is naturally occurred of nanomaterial. Okay, this nanomaterial is occurred naturally in our nature. If you can see the example here, we have the wind erosion. Okay, and then we have volcanic activities, especially from the dust, the cosmic dust, the biomass combustion. All of this is naturally happen. Okay, and then the second one is the man-made nanomaterial. So this is where our focus is. Okay, the material, the nanomaterial has been made or altered by the scientists or physicists. If you can see, this is a few examples of the nanomaterial made by the physicists. First, you can see we have the nanotube. Okay, we have the nanowire, nanofiber, nanoflower sheet, and nanoparticle. We do have a lot of types of man-made nanomaterial. Okay, so why we should use the nanomaterial? Why the nanomaterial is important? Okay, if you can see, firstly, the nanomaterial is faster in terms of the rate of reaction. Okay, I will explain why the nanomaterial is faster in terms of the rate of reaction. And then, of course, it lighter because the size is very small and it's cheaper than bulk. Okay, and then we can fit the nanomaterial in very small space. Okay, so we can reduce a space, okay, and the nanomaterial have highly sensitive or high sensitivity, okay, especially if you want to introduce nanomaterial in sensor as our sensor, okay, and also it having different kind of properties, okay. These properties depend on the size of the nanomaterial, because even though the size range from 1 nanometer to a few nanometer, it will bring a greater impact on the properties, okay. And the last but not least is the large surface area to volume ratio. Actually, the last point here is our main focus, why exactly the nanomaterial is faster in terms of rate of reaction and high sensitivity. Okay, let me explain what is actually the surface area to volume ratio and how it relate to the material, the nanomaterial. Okay, if you can see here, this is example to explain the surface area to volume ratio. Okay, if you see from the first cube here, assume this cube as the material, chunk of material. Okay, before we can cut this cube into a few pieces or small pieces. So let's assume the each of the length here is 4 units. Okay, and then the total surface area where the contact area is 96, because 4 times 4 times 4 and times 6 area or surface here. Okay, while maintaining the total volume is 64, if you find the total surface to volume ratio, you will get 1.5. If you cut this big chunk of material into a few pieces or small pieces of material here, actually you can see the total surface area is increasing, okay, increasing while maintaining the total volume. So the surface to volume ratio will increase. Okay, and if you cut into a very small pieces from the big chunk, as we the total surface area will increase and increase. So more contact surface to the surrounding. So that's why when we have more contact area to the surrounding, it will increase in the rate of reaction and become highly sensitive toward the surrounding. So that's why the surface area to volume ratio is very important factor to determine the nanomaterial itself. Okay, the easy example, if you take the Panadol soluble, okay, if you try to dissolve the Panadol soluble into the glass of water, okay, if you have two setup, one setup you take the big chunk of Panadol soluble and try to dissolve it. It will take a certain amount of time, rather than you cut the Panadol soluble into the small pieces and to try to dissolve. Of course, that small pieces will take a much less time to fully dissolve. That is to shows that the small pieces of Panadol soluble having the more contact area to the surrounding, so it increase the rate of reaction. All right, and then we move on to the application of nanomaterial. What kind of application that we can apply the nanomaterial? First, we can apply into the electronic devices. Nowadays, in our 21st centuries, we have a very small devices such as your phone, the laptop, because the scientists or the physicists already introduced the nanomaterial in these electronic devices. So we can fit the small space, or we can decrease the size, especially your phone, your laptop, okay, because you bring it every day. So it's easy for you to bring a small laptop, right? And then we can apply into the optoelectronic devices such as photodiode or solar cell. Okay, it will increase the rate of reaction. For example, the photodiode, okay, increase the rate of from the photon. Okay, from the photon. Okay, it will increase the production of photocurrent, especially to the solar cell here, right? And then memory devices. Okay, memory devices such as RAM, okay, your hard disk, okay, but the SD card, and of course we can use the nanomaterial in the wastewater treatment, where we apply the nanomaterial as our photo catalyst, as a catalyst here to degrade the pollutant inside the water. So we can have the nanomaterial as a wastewater treatment. And also medicine medicine also we use the nanomaterial to increase the efficiency of the medicine itself, right? So our body can absorb this small material in our body much efficient. Last but not least, also our skincare product, we use the nano material. Okay, especially at our sunblock, the physical sunblock where they use the zinc oxide, okay, to protect the skin from the sun. Okay, now let me introduce to you how we create the nanomaterial, or in other words, how we synthesize, okay, the nanomaterial. So in here, I will introduce three methods where we can synthesize the nanomaterial. Okay, first we have the physical vapor deposition or PVD, and then second one we have the chemical vapor deposition, and last but not least we have the chemical solution deposition. So this three method is very popular for the synthesization of the nano material. So we go one by one here. First, let's focus on the physical vapor deposition. So what actually is this PVD? Okay, PVD is a top-down approach method, meaning that from the big chunk of metal, the target metal, okay, and then we scrape off a few microgram, and then we want to stick it into our sample, okay, from the chunk of material to the nano material, from the big to small. So we call it as a top-down approach method. And the PVD require ejection of the physical material of the atom, okay, from the target, right? So this metal will have some condensation of the nucleation of the particle into our substrate material, okay? And in PVD also certain gases will be introduced to enhance the deposition, okay, to enhance the deposition, to enhance the rate of deposition to the substrate material. Okay, so what kind of material that we can use? So the materials such as metal, ceramic, polymer, composite, etc. can be used as the deposition material. We do have a lot types of material that we can deposit by using the physical vapor deposition. Okay, but under the PVD or physical vapor deposition, we do have the different types, okay, of technique, right? So in order to reduce any pollutant or any particles, all right, so the deposition must be done in high vacuum environment, normally from 10 minus 4 to 10 minus 5 millibar. Okay, so we will have the deposition occur inside the vacuum chamber. So this is the few types of PVD. Okay, under the physical vapor deposition, we have four here. The first one is the thermal evaporation. Okay, if you can see on the right side here, this is the setup for thermal evaporation technique under the physical vapor deposition, where if you see here crucible, we put the crucible here where we put our metal or our target material. So this target material will be heat up, okay, heat up, and then it will vaporize inside the chamber here, and it will stick and adhere to this substrate. Okay, so the temperature we use here must be suitable for the substrate that we use here. Okay, and inside this chamber is vacuum environment, so there is no air particle or any particle will stick to the substrate, so we don't want uh, any unwanted material in our substrate. Okay, and then the second one is the electron beam evaporation, where we use electron beam as rather than we use the thermal. Okay, so the electron beam will become our we evaporate the material. Okay, so we have the hot filament here to produce the electron beam, and then this focusing magnet and deflecting magnet will deflect the electron beam to the target material. So the target material here will evaporate into the substrate here. Okay, so electron beam evaporation also must be done in high vacuum environment. Okay, and then the third one we have the magnetron sputtering. Okay, magnetron sputtering will be introduced the magnetic field inside the chamber. If you can see here, this magnetic field will create the negatively charged. Okay, and then some inert gas must be introduced here to enhance the rate of reaction, and also this inert gas will help to scrape off the target material to the substrate, where the negatively charged here will react and collide with the, for example, argon here. We use the argon as our gases here, and then this electron will collide with argon ion, and this argon ion will accelerate and bombard with the target material, and then this target material will scrape off from the material and then go to the substrate. Okay, our thin film here, and it will adhere and deposit. Last but not least, for the PVD here, we have the pulse laser deposition, where we use the laser beam here to scrape off the material, the target material here. Okay, and then the target material will create a laser plumes, okay, content of species of the target, and then this species will go to the substrate. Okay, all of this must be done in high vacuum environment. So this is a few types of physical vapor deposition technique. Okay, and then let's see what is the second types of uh, technique, which is the chemical vapor deposition. From the word, we use the chemical vapor, right? So this one also is a top-down approach method. Okay, so the coating technique for the CVD, okay, process, normally we use the thermally induced, okay, thermally induced. So we will use the high temperature in this CVD, okay, to create our target material, to scrape off the target material, and then it will stick to our substrate here, right? And then the temperature will ranging up from 600 to a few thousand degrees C. Okay, so the temperature is quite high here, and then this CVD is easy to control the mixture of gases. Okay, remember the gas is actually is as our target sample. Okay, PVD, we will use a chunk of metal itself, but in CVD, we use the gases as our precursor. All right, so this CVD actually it's easy for us to control the mixture of gases if you want to introduce some dopant in your material. Okay, and then the material or precursor used in form of gases, of course. And then we also have a different types of CVD techniques. Okay, so the key measure here for CVD to get the best result, okay, you must control and you must make sure you use the suitable substrate material, because if you can see, we use a very high temperature in our CVD, so the material also must be suitable. Okay, so you need to choose the material, the substrate. If the substrate cannot withstand the high temperature, you cannot use a certain type of material, substrate material. And also substrate temperature must be controlled, okay, inside the chamber. And also the gas mixture, the flow rate of the gas also must be controlled in order for you to control the rate of deposition. Okay, so I will show you a few types of CVD. So the first one is the conventional of the chemical vapor deposition. Normally the conventional one we will use inside the tube, okay, or chamber. But the example here, I'm using the quartz tube. Okay, inside the quartz tube here, I will flow my gas, okay, my target gas, precursor gas here, and then it will flow inside, and then I will heat up the quartz tube. Okay, as I mentioned, this chemical vapor needs high temperature. Okay, so my substrate must be put on top of this quartz board. The quartz board material can be made from ceramic, and other types of material which can withstand high temperature. And the sample or the target substrate must be put on top of the quartz or any types of boards here. Okay, and this quartz will be heat up. All right, and then the environment will heat all the sample, and it will go to the target, the sample substrate. Okay, and this is the conventional where we use high temperature. And then the second one is plasma enhanced chemical vapor deposition. Okay, plasma enhanced and conventional actually still use the gases, but plasma enhanced is introduced because we want to reduce the temperature of the substrate, because some substrate cannot withstand the high temperature. So the best way is to control the temperature or reduce the temperature by introducing the plasma. Okay, so that's why by introducing the plasma here, the plasma will react with the gases, okay, with the gases species, and then the temperature can be reduced. So we can use a few types of other substrate, and then you can uh, get the target what you want lah. Okay, and then last but not least, we have the laser induced CVD, where we use the laser to scrape off the some of the material, and then it will go to the substrate. Okay, it will deposit onto our substrate. All right, and then the last technique here is the chemical solution deposition. All right, chemical solution, of course we use the solution as our precursor, okay, to put into the substrate. Okay, so chemical solution deposition is the coating technique which involves the usage of chemical solution. All right, you need to prepare the chemical solution as your precursor or starting material here. So CSD or chemical solution deposition is cheap because we are not using any machine, any device. Okay, so this is cheap to prepare, and this one easy also to prepare. Okay, and easily to control the stoichiometry ratio where you want to introduce the dopant. So you can easily to control, okay, the ratio of your precursor. And of course, no need sophisticated equipment. You don't need the vacuum chamber. We don't need any types of plasma, okay, laser. So you can prepare the material in the just in the lab, okay, and also you can yield a fast result and also sample and easily being prepared in any surrounding or ambient surrounding, because we don't need any high vacuum environment to prepare and also to coat the material. Okay, so here is a few types of the chemical solution deposition here. The first one, we have the deep coating, where you dip your substrate inside your precursor solution. Okay, you prepare your solution, your precursor solution first, and then you take the substrate and you dip. Okay, you dip, and then the thickness of the coating here being controlled by how many dip. Okay, maybe you dip one time, two times, three times. You want to control the thickness, right? And the second one is the spin coating. Okay, spin coating also you need to prepare the solution, the precursor, the starting material here, and then you spin your substrate. Okay, once the substrate is being spinning here, and then you drop a droplet here of the solution, and then the solution will spreading out. Okay, due to the rotating or rotating your substrate, and then this substrate will be evaporate. Okay, you will heat up this rotating substrate here, and then it will stick on your substrate. Okay, and then we have the co-precipitation. Okay, co-precipitation, we will use high alkaline solution here, all right, and then to create the precipitate of the nano material. Okay, also use the chemical solution. So this precipitate you will collect by dry in the oven. Okay, and then you will get a dried sample of powder of nano material. This one normally we want to collect the in terms of powder. Okay, in terms of powder, because the rest we use the substrate. And then we have auto combustion salt gel. Okay, where you create the solution and also the solution become gelation. So that's what we call as a salt gel. Also, we start with the mixing the precursor. Okay, mixing the precursor here, and then you will put the fuel. Okay, fuel, for example, the gelatin agent. Okay, and then it will be heat up until become powder. They also in terms of powder, your sample in terms of powder. Okay. And last but not least, we use the spray pyrolysis, where we use the atomizer to spray our solution into the substrate. So this substrate will be heat up until working temperature, and it will stick on top of this substrate. So this substrate will become a thin film. A thin film will deposit on top of this substrate. So this is a few types of chemical solution deposition technique. So I think that's all from me, especially the introduction to the nano material. Okay, thank you.
Oh, okay, so thank you very much, Dr. Helmi, for the interesting talk about the nano materials. So, guys, be inspired, be empowered, join MAHSA University, and make a difference. Thank you.